Hello everyone, my name is Jiaying Zhou. Currently, I'm working at Group as a senior staff engineer. Today, I'm going to talk about using Ray on large-scale applications at Group. And I will show you what kind of problems we have met and how to use Ray to resolve the problems. Okay, I will represent the talk by three sections. Firstly, I'm going to talk about the big data scenario at Group, and then I will talk about why we choose Ray as our basic computing framework. In the last section, I will use some real-life cases from our business and show you what we did in Ray. And how to use Ray to support our requirements. Okay, firstly, I will introduce about my company. The Ant Group is the largest FinTech company in China. Our business includes many areas such as online payments, lottery, and the insurance. On the other hand, in order to operate this financial business online, so we need to build many capabilities, such as online promotion, risk controlling, and high stability payment systems. Therefore, we need massive data to help us to make intelligent financial decisions, analyze financial trends, and use AI to support business requirements. So we need the ability of building powerful distributed system that can handle a massive amount of data. Okay, then let me talk about the typical scenarios in massive data computing. Here we have three scenarios of data computing: the machine learning, data analysis, and online decision. In here, I will majorly talk about the online decision. So yes, traditionally, we use simple rules to make financial decisions. Those approaches won't work anymore, as we need to process a huge number of transactions every day. Today, our system need the capability to process complex rules in very short time. For example, in hundreds of milliseconds. So we call this scenario for online decision. So that's why the data computing is very important to us. Yes. Okay. Now let's talk about today's landscape of computing. As we know, we have many of computing systems to choose from. For example, if we need to do an interactive bench job, we can use Spark. If we want to process data continuously as a flow, the most popular one must be Flink today. Right now, we can find out the most suitable computing system in every computational pattern. By computational pattern, I'm referring to the data process paradigm, such as bench and streaming. So concurrently, engineers usually tend to fit their real-life data processing scenarios of these patterns. But in real life, a business scenario may contain multiple complex steps of data processing. Take a machine learning application, for example. We can see the whole pipeline usually contains 5 components. So if we want to build a machine learning application, we have to use many different systems together. For example, we can use Flink to process streaming data, use TensorFlow to train the module. Then here's the problem. We have to transfer the data many times between different systems, which will cause some more storage overheads. And in addition, multiple systems result in multiple programming paradigms and require expertise in different areas. So the learning curve will become more steep. Besides the problems caused by multiple computing systems, we have made some issues on other sides, such as performance, flexibility, and stability. First, regarding performance, in the online decision scenario, we often use RPC service to receive user requests. And normally we have to respond to the request in short time. In production, usually we need to make sure the latency is less than maybe 200 milliseconds. Besides the performance issue, another issue is the complexity of developing distributed applications. As we know, traditional computing system majorly focus on data processing in a specific computational pattern, such as RDD on Spark. But if we want to develop the application, which is mixed with data processing and business logic together, it can't be fit into a specific pattern. So eventually, we hope to build a distributed system. The system should include multiple computational patterns, and engineers can use the different patterns to build any complex application. In addition, we hope all these patterns can be built on a general distributed computing engine, and it can be easily plugged on the engine like a plugin. And the data can be shared among the applications on this engine as possible. Yes. And besides that, we hope the system can allow us to easily develop the distributed business logic, so engineers can build the complex distributed application with minimal effort. Yes. Then let's go into the next section. Why use Ray to build our distributed system? Okay. First of all, let's see the Ray's introduction again. Ray is a faster and simple framework for building and running distributed applications. Okay, the keywords here are fast, simple, and distributed. These features seems to fit into our expectations. As we know, Array uses actor and the task as smallest units to develop the applications. So Array can provide more flexibility than the other distributed systems. Yes, that's very cool, and this we need. So based on the recall, we have developed a few distributed framework as a plugin. Each of them implements a computational pattern on the recall. For example, we have a real-time framework, which is a streaming library that processes data continuously. And also, we have multiple parallel processing framework that can process the massive data in parallel in a short time. And the AI framework will support the third-part machine learning training engine running on Ray. Currently, we can support the TensorFlow running on Ray. And the last one is the service module. It can open an online service on Ray actor and can deploy any application into the service. Okay, besides these frameworks, we will provide some deployment features under the recall. First, we deploy the Ray on Yarn deployment, and then we build the Ray Kubernetes operator to support running Ray on Kubernetes. And we have also built some features about scheduling, such as auto scaling and HPA. Okay, so this is the race architecture at OnGroup. Okay, now I will show some real-life scenarios in the OnGroup. Let's start with online machine learning. Okay, in the beginning, I'm going to talk about the difference between online machine learning and traditional machine learning. As we know, the machine learning system usually use offline data to train the module, and the training phase may take more than a few hours. At last, the mode the mode was updated to production and will be served. So, so there are some problems with traditional machine learning. One is only using offline data to train the module, and the other is long training time. Yes, but in many cases, we need the machine learning system to train and serve model faster. For example, we have many marketing promotions every day, and promotion action may only last less than 1 day. So if we use traditional machine learning, we can use the real-time data to train the module and can't update the module quickly enough. Because of those reasons, we wanted to build an extremely fast machine learning system to support our business. We call it in online machine learning. And the system can read the real-time data, train model faster, and speed up the module iteration cycle. Okay, on the other hand, as we know, there are some online learning applications building on top of Spark or Flink systems. And they use message queues to connect the data processing and the model training components. But it has some problems. First, it use queue to transfer data, which may lose some data during system failures. And second, because we need to glue different systems together, so they can't keep a consistent SLA. So in here, we also care about some other features such as stability and development efficiency. Regarding stability, we must make sure the system can't lose any data in production, not only in the data processing phase, but also in the training phase. And in the whole pipeline, it's better to follow up one standard SLA to keep the availability. And regarding efficiency, we want to develop the pipeline only in a single platform and use simply code or SQL to build it. Yes, that is a kindly way to engineers and data scientists. So yes, we built a machine learning system on Ray. This system includes two tiers. The one tier is online machine learning framework, and the other is recall. So here we will focus on the online learning framework right now. So in their framework, it contains three components: real-time distributed training and the model serving. Okay, first, in the real-time components, it provides some streaming functions such as DAG pipeline, task status backend, checkpoint to recovery. And in addition, we can use streaming API and SQL to develop a real-time job. Yes, and in the training component, we're supporting running TensorFlow framework on Ray. Also, because of the real-time is based on Java, but the training is on Python. So we must combine the two different language workers together, and they can transfer data between each other. In order to do that, we designed a job master who can create Java and Python actors when streaming job starts. And last one, we provide RPC service on Ray. In this case, we can build module prediction service on one job. Okay, finally, let's look at the full pipeline on the online learning system. Okay, in runtime, we can see there is a streaming deck in the beginning, and after the join nodes, the data will be trained as a mini bench. And lastly, the module will be deployed on a service node. So other applications can request the prediction service via RPC. And then we provide two ways to develop an online learning job for engineers, the data streaming API and the SQL. Yes, in this slide, we can see how to use SQL to develop a job. In the first half, it used the standard streaming SQL. We used the two data source and joined them by trace ID. And in the second half, we expanded one keyword train. It connected the streaming and the training job, and the means of that flow data as input to TensorFlow for training, and output module to the specific path. Yes. Okay. After the online learning scenario, I'm going to talk about the scenario of complex online decisions. Unlike online learning, which is used in AI area, the complex decision could be used everywhere, such as AI, business applications, even like UDF in other computing systems. So let's take a look example of online application. Okay, in this application, we have an online service. The service receives an error as a parameter from other application. Then we will look over the error and use each item to request another service and to get some data. And then we will use the data to query storage and to do some computation. Finally, inside the loop, we will merge every result and return to original request. Because it's an online service, we want to make sure the total latency is less than 200 milliseconds. In real life, we have three challenges in this case. The first one is how to dynamically process data in parallel, and secondly, we need flexibility of handling various computational patterns. And the last one is that we want to convert a latency non-distributed program to a distributed program as simply as possible. Yes. So in order to resolve those problems, we built a massive parallel processing framework on Ray. We call it MPP. Yes, the framework has two tiers. One is the API, and the other is runtime. Firstly, I'm working. I'm going to talk about API tier. In this tier, we offer two API styles for developers: Java API and SQLite. For Java API, we want the developers can build a distributed application like a traditional Java application. So we provide a set of distributed Java utilities, such as distributed linked list, hash map, and iterator. At the same time, we also have a specific annotation to mark a method as needing to be executed distributedly. And in SQLite, this can use like the SQL to process the amount of the data. And under the API tiers is runtime. It includes some functions module and provides the core of runtime. So let's start from code compiler. Okay, the code compiler is responsible for analyzing the user code and find which parts can be parallelized with array. And after that, we develop a BSP pattern in this framework. It can be ensured that the program will continue to the next step when every subtask is complete. Besides that, we provide a series of data aggregation functions, such as count, sum, group by. Okay, so if we want to process the data as a batch, we can use them. And the bottom is MPP core. It contains some rules in a job, such as a job master, coordinator, a service proxy, and so on. And the core is also responsible for splitting a task and scheduling the workers. Yes. So at last, I will show you how to use the MPP framework to build an online decision application. Firstly, the business requirements is to process the data of the last 2 hours and return the result in 200 milliseconds. That's very important. The amount of the data about 10 megabytes per second, and the time window range is between 1 second to 2 hours. So we must design an application to process massive data in a short time. In order to do that, we build an application which combines the real-time and the MPP framework. The real-time framework builds the DAG job to read and shuffle the flow data. And after that, the MPP framework is responsible for querying and processing the data in parallel and open a service to receive requests from other applications. Besides that, in this application, we want to speed up the processing, and we implemented the dynamic scheduling with reactors. So we combined the real-time sync and the MPP workers as one actor. At the same time, we store the data in memory cache that process and flash them to persistent storage regularly. Okay, to ensure processing data as quickly as possible, and we don't need worry about losing data. At least in real life, we can process the data that has more than 10 million dimensions in 200 milliseconds. At the end of the presentation, I want to talk about the goal of data computing in my company. Through the previous introduction, we know our data processing scenarios are complex. We want to build a computing system which can support different complex scenarios. So we designed a distributed system and includes many computational computational patterns as plugin on it. So we gave this system a name, fusion computing. Based on this system, we can develop new computational patterns easily and fast. For example, if we need to support a complex computing scenario in the future, we just need to combine different patterns. Instead of developing a new system from scratch or gluing many systems together, and for developers, they can build an application via the specific patterns API and the Real Native API together. Okay, the system provides flexibility for development and efficient computing power. So that's the goal of computing system for us. Yes, that's all. Thank you.